Just 10 miles from the Gulf of Alaska, the Wrangell-St. Elias Mountains are the tallest coastal range in the world, and they are getting taller.
In the St. Elias range, there's very, very active mountain building going on. And so you have to be pushing those mountains up very fast in order to get that much rock that high, because erosion is always trying to tear things down.
The mountains rise because of movements of the Earth's crust, which is made up of large masses called tectonic plates. Plates often collide or slide underneath one another. Growth in the St. Elias Range is the result of a tectonic plate pushing against a small piece of the continent called the Yakutat Block. At the Geophysical Institute at the University of Alaska Fairbanks, scientists are studying tectonic motion. It's part of STEEP, the St. Elias Erosion and Tectonics project.
Under most of Alaska, the Pacific plate is being pushed underneath the North American plate. In this case, you've got basically a little piece of material that's kind of been shoved into the corner and doesn't want to go down. And that's actually really what's pushing up the mountains, basically, is the force of this collision is what's building these mountains and what has built them over the last few million years.
But the movement of tectonic plates causes more than mountain growth. Earthquakes, volcanic activity, and ocean trenches all occur along plate borders, and scientists who study each area are involved in STEEP.
This is a multidisciplinary project where geologists go and want to understand these collision processes. They want to understand the erosion aspects of what's going on. And we're trying to help by finding out where these active faults are that are being caused by this large collision.
One of the ways STEEP researchers hope to learn more about tectonic activity in Alaska is by studying active fault lines. Already, they've had surprises.
A few years ago, we found that after effects of the 1964 earthquake were still measurable today, that we still see motion of parts of the Earth that was triggered by the 1964 earthquake. Never expected to see that 35 to 40 years after the earthquake.
Your ability to pinpoint exactly where an earthquake occurs depends on the density of stations that you have to locate it and to record it. And the network we had before this experiment was very sparse.
So there's several things that the STEEP project is trying to do. In the first place, it's simply trying to explain what actually is going on in this region. Where are the active structures that are bringing up these mountains?
To answer some of these questions, scientists from the University of Alaska Fairbanks are using two important tools to collect information: seismometers and GPS technology.
To record earthquakes, you don't know when the earthquakes are going to be. You can't just put a seismometer out for a day or two and expect to record what you need. So you need to put it out for a long period of time. So what they're doing is they're putting basically what they call a vault, which is just really kind of a fancy name in this case for a yellow garbage can.
The yellow garbage can vaults contain a seismometer that picks up vibrations from earthquakes. Using digital transmitters powered by the sun and wind, information travels to a satellite uplink. From there, data are uploaded to the internet, so information from the STEEP project is available to researchers around the world almost instantly. The other key to the region is large-scale tectonic movement that scientists are tracking using precise GPS measurements.
All we put in the ground is most cases, a stainless steel pin about this long. So we'll find a nice good piece of rock, drill a hole, and just use some epoxy to put in this pin. And the pin has a little mark on it, and that's the point that we're going to resurvey on a every year, every other year basis or so. To some extent, there's probably going to be some things coming out of this project that we can't really predict. And that's the way research is. You're starting to look at something new, and you don't know where it's going to lead you. So there are going to be some things that we may not be able to see right now. I think in terms of approaches, we should, at least our aim, is to combine data from many different fields in a way that has rarely been done before.
As each individual group works together and brings all their pieces of the project together, we'll be able to synthesize a model and an understanding of this plate tectonic action that will probably be usable for many of the places throughout the planet.
STEEP's goal is to develop a scientific model that describes the interaction of tectonic forces and erosion. But discoveries in this one remote region of Alaska will contribute to a greater understanding of the hidden forces in our world that can literally move mountains.